This is Professor Miller, and this is a little example of a hypothesis test. So the mean math score on the SAT is 511 with a standard deviation of 109. Those are known facts. But Joe has this tutoring service that he thinks can increase students' test scores. It's nice that he thinks that, but we'd like to be more sure than that. Let's do the math. He tutors 32 students, and after the tutoring program, his students have a mean SAT math score of 544. Conduct a hypothesis test using alpha of 0.025. We'll talk about alpha in a little while. The setup for the hypothesis test begins with this thing called HO, the null hypothesis. HO, or null hypothesis. In this case, the null hypothesis, null means no or none, would be that the mean, and this is the mean of all tutored students, the mean is still 511, that the tutoring has no effect, null hypothesis. The alternative, see, we sneak that in below, it's what Joe really wants to prove, is that the tutoring increases the students' scores. Now notice I don't put the 544 here. It's not that Joe thinks his students will score on average 544, it's just that he thinks they'll score higher than everybody else. Logically, I want to go back and make a little adjustment. I'll make this one less than or equal to, so that if one of the statements is false, then the other one must be true. They're complementary events now. Well, if you've been following along in the course, you can guess what comes next. Draw the bell-shaped curve. Interestingly, it doesn't say anywhere that the SAT scores are normal. They probably are. But in fact, we can draw the bell-shaped curve because of the central limit theorem. What goes in the middle? Hopefully you would say 511, but there's a little bit of a thought process as to why that's in the middle. If you think about it, what we just did was assume the null hypothesis to be true. There's this little analogy that's used to describe hypothesis testing. It's analogous to a trial by jury. And there's this presumption of innocence, that I'll believe what my detractors say about my program until I can prove beyond a reasonable doubt that the other hypothesis is true. This alpha has a lot to do with that reasonable doubt. It's sort of our level of a reasonable doubt. So clearly we're to the, all the action here is going to be to the right of 511. The question is, where is this 544? Is it just a little bit more than 511 like this? Or is it so much more than 511 that we can say beyond a reasonable doubt that these students score higher? So again, this alpha is the area in the tail associated with HA, and it's this level of what it means to have a beyond a reasonable doubt. In the trial analogy, think about this, it's the probability of hanging an innocent person. So we draw this picture under the assumption that they're innocent. We get our evidence. If our evidence comes out up here, we're going to say that they were guilty, and yet they were in fact innocent. It's possible to get a mean this high under these conditions, but very unlikely, and that's why we keep alpha at some small probability. Okay, so where is the 544? Well, first of all, that alpha, putting that in that tail, sets off a little chain of events. If you think about the normal curve, if alpha is 0.025, this area is 975, and that gives me a cutoff score in terms of Z. I'll show you that in a minute. It's 1.96. That's called Z crit. If you consider this area below a certain Z score, using Excel, using the norm's inverse function, we can find that we need a value of z beyond 1.960. Again, from the very beginning of the course, I've been emphasizing more than 2 standard deviations away from the mean is weird, and Joe needs this outcome to be weird. Any group of 32 students is going to give me a mean conceivably different from 511, but how significant is that difference? That's what hypothesis testing is all about. So what's left to be done? We still need to determine which placement of the 544 is the correct one, close or far. A couple ways to do that. First way I'll show you is finding its z-score. By the way, this axis is the distribution of all possible sample means, x bar. Most important formula in this course, x minus the mean over the standard deviation. But since, as I just noted, we're talking about the distribution of sample means for all groups of 32 students, put a little bar over that, and the square root of n goes down here. So what do we have? 544 minus 511 over the standard deviation that was given by the College Board, actually. Square root of 32. 33. You can flip this and multiply. .71. Aha! 1.71 is relatively close to the 511. So this 544 is the correct placement. See it? It's not more than 2 standard deviations above the mean. Most important in this problem is the conclusion. You need 2 parts. First, which of these 2 statements, the HO or the HA, do we believe at this point in time? So actually, we do not have enough evidence to believe HA. The way we state that is fail to reject HO. It is not far enough away from 511 that we can say for sure that the true mean of all tutored students is not 511. It's just not that far away. And that's the next part. We need to say something about the SAT test scores. Joe's sample mean of the 32 tutored students is not, I can't say it's not higher than 511, but it's not a statistically significant difference. Not significantly higher than the SAT score of all students. Okay, so that's what's called the classical approach. Let's take a look at Excel. So what I just showed you was first we needed z-crit. To find z-crit, we had alpha equals 0.025. So I'm going to use the norm's inverse. Again, the 0.025 is in the right-hand tail. The way this function works is based on the probability below that, 0.975. Okay, that's 100% minus 2.5%. That's the 1.96 that I was using as the critical value. That's this line drawn in the sand. Is Joe's mean above that? Then we can say the tutoring works. If not, it doesn't. Well, we don't know for sure that it does. Let's say that. 544 was his sample mean, and that was the sample mean that he found for 32 students. And so I used the formula for the z-score, and I found 1.712. Another way to see the same problem in a different way, you come up with the same conclusion, is to look at what's called the p-value. And that is, rather than comparing z crit and z star, we compare the probability of getting a sample mean like Joe got, compare that probability to alpha. So what we're going to do here is find the probability associated with the sample mean that Joe found. Well, we found the z-score, so I'm using Norm's test. That's not right. That's not comparable to alpha. That probability is the probability to the left of the z-star. Okay, so that is not the correct p-value. What we need to do in this case, not always, but because of our diagram, we realize we need to subtract from 100%. Okay, so there was about a 4% chance of getting, just by luck, a sample mean like Joe's. Okay, so another way to look at this is called the prob-value approach. Same problem, just a different way of reaching the conclusion. 511, 544 was here. Find its z-score, 1.71. First I found this area. I needed this area. And that was 0.0434, and that was found by doing 1 minus probability associated with 1.71. That is called the p-value. Actually an important takeaway from the course. Most statistical research studies that you read will just show you that p-value. It's actually a good thing because you don't have to rely on somebody else's alpha, what they feel is an appropriate level for beyond a reasonable doubt. You get to choose whether you're comfortable with the result and your level of a reasonable doubt. So that's about a 4% chance. Now, alpha is smaller than that. So that is greater than alpha, which was 0.025. So then the same conclusion. You don't need z-crit in this case. When you're doing the p-value approach, you compare your p-value to alpha. In this case, since the p-value is greater than alpha, we cannot reject HL. So one of the most important takeaways from this course is that a small p-value means that you found a highly significant difference. Here the p-value is bigger than alpha. Our z-star was smaller than z-crit, and it's equivalent. That's an introduction to hypothesis test. There'll be lots of little variations on that theme as we go along.